now let's talk a bit about structured outputs. So up until now, we've kind of seen that the output to our network is a probability distribution. That can be quote-unquote boring, right? We might want to do something more rich with our network. So structured outputs is one way to do some more interesting predictions with our neural networks. So in short, structured outputs allow us to do multiple predictions, but that relate in one way to the rest of the predictions. So for example, for the case of classification, they don't necessarily relate to one another. But if we have an output that's an object detection bounding box, right, these 4 coordinates that we'd be predicting relate to one another in that they are related to the exact same box. So there are different types of structured outputs that we usually find. So here we have, again, the classic classification thing. So we give our input to our network, which is an image of a bicycle, and the output is just the category bicycle. But if we have an object detection pipeline, we give the bicycle as an input, and our neural network will now predict the bounding box of this object as well as what's contained inside it. So here our network will give us the coordinates to this bounding box as well as the category associated to it. Finally, if we want to go into a bit more fine-grained detail, we can also get our networks to give us segmentation masks. So here, if we give the input to our neural network, it'll then give us a segmentation mask where pixel by pixel, it'll say this pixel belongs to the bicycle category, this pixel belongs to the background category, etc. So let's look at how we might do this in practice. So for bounding boxes, in the case of object detection, a bounding box typically consists of 4 xy coordinates. So if you wanted to define this box, you have a point here, a point here, and point here, which would give you a total of 8 pixel coordinates. But if you say, well, we're dealing with a box, so let's just talk about, let's use the representation of a box. It turns out that you can represent any rectangular box with 4 coordinates. So in the case of the SVHN dataset, the Street View house number dataset that we looked at earlier, if you look at how the data is constructed, they give you the x and y, so that the top left coordinates of the image, and then the height and the width of the box. So now you have a total of 4 coordinates instead of 8, and this is enough to represent a box. So you can train your network to output the coordinates to the box instead of outputting a probability distribution. So how do we evaluate if our box is good or not? You can think that there can be many, many different boxes, and if we impose on the network that it had to output the exact box, that could be problematic. We need a way to sort of say one box is better than another box based on some kind of metric. So a widely used metric is the intersection over union metric. So the way that we calculate this is we take our original box, we take our predicted box, and we compute the area of overlap between the two, and we divide by the area of union over the two. And so this ranges between 0 and 1. 1 is complete agreement between the boxes, and 0 is complete disagreement between the boxes. So let's look at an example. Our green here is our ground truth. Suppose we predict the red box. So you can see here that the red box is very close to the green box. So now we can measure our IOU, and we might say, well, we have approximately 0.9 IOU, so this is a very good box. This box is in agreement with what we would expect. If we took another box that might contain part of the bicycle but not most of the bicycle, this will be a bad, quote-unquote, bad overlap. So now we would have, say, for example, 0.4 IOU. We got some of the box but not all of the box. So this is a way to evaluate how well our boxes have performed. And a reason why, again, this is important is because suppose you have someone annotating these boxes, they might not be perfect at annotating the boxes either. So there was a question earlier of how do you deal with noise? Well, this is one way that you can deal with this noise. Instead of saying the box has to be exactly as what was annotated, you just say it has to be as close as possible to what was annotated. So now let's look at the segmentation mask. So the segmentation mask classifies pixel by pixel in the image as belonging to a certain class. So, for example, in the case of this bicycle, we have a mask here, and it would really be a kind of binary mask. So for each category, you might have a binary mask saying, these are the pixels that correspond to the background, and these are the pixels that correspond to this specific categories. And of course, these segmentation maps can be overlaid on top of the original image when you're doing your predictions. to then see what your network predicted as being part of your image or not. So there are different types of segmentation. There's what's called semantic segmentation and instance segmentation. So in the case of semantic segmentation, we don't distinguish between classes, between objects in the same class. So here's a neat little example. If we're trying to distinguish between bottle, cube, and cup, you see that we're able to distinguish between the different classes properly, but here we don't have a distinction between these two cubes, whereas we know that when we look at the original image, there is a separation. So in the case of instance segmentation, we see that we actually have this separation, and you can imagine how this could be useful if we're trying to identify multiple objects in the same image of a same category.